Hello and welcome everybody to Advent of Code 2022 Day 12. So today it's kind of a fun problem. It's not super complicated. There is an algorithm that if you're familiar with it, it'll make this go pretty efficiently. But it's not strictly a requirement. You could solve it in other ways and you'll still be able to get the problem out. It's not going to be an impossible task to complete it. But with that algorithm, if you happen to know it, then you can make pretty short work of this problem. Isn't that right, Kat? Yep. There you go. So the algorithm in question, that if you know it will save you a lot of time in this problem, is Dijkstra's algorithm, which is generally used to find the shortest path between 2 points in a weighted directed graph. So yeah, this is like often used as an example, as like kind of a classic CS example for, you're trying to navigate through. If you have a map system that's modeled as a weighted directed graph, you can use Dijkstra's algorithm on it to solve the fastest path you should take. So the example is like, well, this is maybe how you path plan for a GPS or something like that. You can use it here, and that's what I ended up doing to solve the problem. So anyway, let's go through what our problem actually is. Day 12, hill climbing algorithm. So you're basically trying to find your way back to the elves, and you're wandering around. You look at your device, and your device has a map of your surrounding area. So you know your start point, and you know the point that you want to get to. And basically you have to solve the shortest path to get from one point to the other. So this is your example input that you have here. What? You want to go out? It's freezing cold out there, Kat. All right, come on. Go on. The window's open. Go out. Yep. This crazy cat's just making me cold here. Anyway. Crazy. Go on. There you go. Apologies for that. Anyway, so we have our map here. Basically, each character in this represents the height at that point. And we're told that we want to navigate from this capital S point to the capital E point in the shortest path possible. But there is a catch, and that is how you navigate around. So you can't go diagonally, you can only go up, right, left, down from any point. Also, you can only go from a point that is at most one level higher than the point you're at. It says you don't want to get your climbing gear out to do it. So you can go from an A to a B, and you can go from a B to a C, but you couldn't go from a B to a D, for example. And you can go down as many as you want. So you could go from a C to an A, for example. You can take as many steps down as you want, but you can only go up one step at most at a time. And that's pretty much it. Yeah, and we were told we want to find the shortest path to do that, obeying those rules. And yeah, here's the example of movements you can make. And you can see here, you sort of start here, you snake your way around, and then you end up in this like spiraling path up to the top point there. So, with that said, let's see how I solved the problem. For the starters anyway, I read in the file line by line, and I create this map. So in my case, my map is a 2-dimensional array. For each cell of that array, I replace the letter that's on it with a number, just as makes the next part easier to do the computations on. So if I get a capital S, which is my starting location, I throw a 0 in there. That doesn't actually need to be a 0. Could just be the height at the location, but I just did it with 0 because I thought it was a little bit logically easier for me to work out. I then also have the point E, which is another special point, and that's the end point. We're told that the end point has a height of 26, which is, so it basically should match any other letter Z that you might find. So it's a high point on the map. But in this case, so that I had a difference between any other high point and the final high point, I set it to 27, because there's no other way that we can have a 27 on the map, so you can make it specific. Then for everything else, I did this operation down here, which this returns the ASCII value for a single character string in Ruby, and I'm minus 96 off that, which will give me A is equal to 1, B is equal to 2, so on and so forth, up to Z, up to 26, just to make it handy. This almost harkens back to, I think it was day 1 or day 2, where I created a hash map of all of the characters, which you didn't really need to do, because this operation here would have done the exact same thing for us. But yeah, that was my overkill solution then. This is the improved version of that here now. So yeah, I do that anyway, and I build a map. So instead of a map of characters, I now have a map of all of those integer height values in it. Then so basically you need to find start and end coordinates. This is helpful later on. I'll explain why. But for this, I just really lazily loop through the whole two-dimensional array. If I find a 27, I know that's my end point. If I find a 0, I know that's my start point. And so then I can just save those off to variables that I have to start with. I then create, so this is where we start the implementation of Dijkstra's algorithm, basically. Essentially, it's a recursion that I'm doing. So you're pretty much walking through your entire map recursively. Up here, I'm maintaining a list of all the points that I visited along the way. So all of the coordinates that I visited along the way. And that is one of the things that gets fed into the recursion. At the very end then, this visited hash will contain all of the points I visited and the shortest distance from the initial starting point to that point. So all you have to do at the end then to find your answer is you just need to look up the end coordinates, which I already know from up here, in that hash, and that will give you the shortest distance to get there. So that's all a bit of a mouthful, but the real guts is in the Dijkstra's algorithm part, which is this recursion down here. So this looks a little bit nasty, but we'll talk through it. It's not too bad. So the first thing we do when we enter into this first loop of the recursion, we know our starting point. So let's say it's 0, 0, pass that in. We have our map passed in. Steps is how many steps it's taken to get to that point in the recursion, basically. And then visited is our visited hash. So we can ignore this first line, because for a first iteration of this, it's not going to be relevant. Basically, this only enters if you've already visited a point. It becomes important. But if you've never visited that coordinate before, you save off the coordinates with the number of steps that you're currently at. I then extract the value from the map of where I currently am. And I will exit early if I'm at 27, because I know that 27 is the very end point of my map. I've gotten to my destination, so I can exit. And if I'm exiting, that'll be at the bottom of the recursion, and we'll exit all the way up to the top then. So if we're not at 27, we're at some intermediary point, we need to calculate our moves. So our moves are calculated so there's an up, down, a left, and a right. The logic that's in here is just to stop my arrays overflowing, which is fine. I've decided that if I get to the edge of an array where it would overflow, I return a value of 30, which is a larger jump than you could make. Could be whatever, 28 or something, 29, 28. So it's enough anyway that you can't ever jump that high. So it's almost as if we've built a cliff wall all the way around our actual map that we have. So anyway, if it is within the bounds of the array, we just extract the up value, the down value, the left and the right values. So we have all those to hand. Then with each of those to hand, essentially what we're trying to do now is we want to go to that point if it's a valid point that we can go to. So the way we know it's a valid point to go to is we can do this check here, which is a little convoluted, but basically we subtract the two values, the two height values we're at, and if the difference between them is less than 2, so that means that it's 1 up or any number down, any negative, so you can jump down as much as you want, you just can't go up, then we can go to that point. Or, and this is a special case for the very end condition, because I chose 27 to be my peak point. If I was, say, at a 26 height point, I could just move over because it's the same height to my end point. But say I wasn't, say I was at a 25 height point, so that's a Y point in the map. You can go up to the endpoint Z, but according to my arithmetic, you can't, because that would be a jump of 2, which is not allowed in my case. So what I've done here is just special case that point that either it has to be within 2, or the current point has to be 25, and the next point, the target point, is 27, which just means it's the last jump that's possible. So that'll allow that case. So basically, you do this for every single point that you can go to, and you effectively update the visited array, or the visited hash, for every single one of those. So what happens then? We're inside this. We've updated our visited array, our visited hash here. We've ended up down here. We've decided that we are allowed to jump to this next point. So we jump into the recursion. We enter back up here again. And that will continue looping until we get to a 27, or until we get to the very bottom and there was nowhere that we were allowed to go to. So there's nothing can happen, and eventually we'll just exit out. So we've basically cycled around, visited all the points, and we haven't ended up at the end point. So eventually we'll just exit because there's nowhere to go. Now, what's going to happen is, this is where this becomes really important. So far what we've done is we've just thrown the number of steps it took to get to that point into the hash. But what happens now, this is the key point here for Dijkstra's algorithm, is that we need to update that value so you don't want to constantly re-enter into parts of paths that you've already done before, unless the amount of steps it took you to get to that point is now less than it previously was. So if I'm at a point XY, I enter into it and I look at the visited value and it was, say, 6. So it took me 6 steps to get to there. So I look at that visited value and I look at my current steps. And if my current steps is 5, that means that I have another path to get to this point that is shorter than the previous one. So I then update the value with that shorter path, and then I recompute the steps again from there to start recalculating. So what'll happen is you essentially start at one point and you start fanning out across your entire graph, figuring out and re-updating points as you find shorter ways to get to those points. The end result of this is that once you've finished the entire recursion, the value associated with each point is the shortest distance it would take you to get from a starting point to that point. So when you look up the end coordinates, there you go, you have it all done. So you can look this up if you want to convince yourself. There's like nice animations you can find of this. My code isn't the cleanest here, it could be a lot neater, but that's the guts of what we're trying to do with it anyway. So we can run my first part code, and it's not super fast. It takes, for my input, it takes just about a second to run, which is relatively slow. But yeah, there's plenty of optimizations you could do in here. I do some inefficient things in this. You can make it faster, but for the purpose of this problem, I'm happy enough to have it solved in 1 second, and then figured that for the second part, it wouldn't be too much more difficult. So let's move on and have a look at the second part then. So they've told you that for the first part, you have a start point and an end point. The only thing they've done for the second part to mix it up is you're trying to figure out what is the shortest path from any point on this map that starts at the same starting height, which is A. So instead of having one single starting point and working at the shortest path to E, we have multiple starting points now. So any point that's in A, And from any of those, or for each of those, we want to figure out which one has the shortest path to E. So it's pretty much the same. We can use our same exact piece of code, everything as it is. We just execute it multiple times. And that's exactly what I did. It's not very fast. So we have, I'll go to my second piece of code. It's more or less the same. I built a map in pretty much the exact same way, except that as I iterate through it, instead of just finding my endpoint and my start point, I find my endpoint coordinates, but then my start point coordinates, those are a list now instead. So as I iterate through this, I just find basically anywhere where my height is equal to 1, and I stick those coordinates into a list. I then iterate through that list of all those coordinates, and I run the exact same Dijkstra's algorithm for each coordinate in a row, and then at the very end, I find the smallest value that's there. And that's it. So it's the exact same. It's just, so it's a little slow in my case is all. And the reason it's slow is because it took about a second to do, it took about a second to run the first part. You notice there it just did a big whoop. Because some of the paths are very quick to calculate, some of them are shorter because that's naturally the way it'll work. But yeah, so it's a little slow. It does get there. I think this takes about 2 minutes to finish, but it does the job, and it's not a crazy depth. When I tested this and it wasn't really doing anything, I started outputting this and looked at how fast it was running through, and I said, well, this is a reasonable amount of time for me just to sit and just watch it churn to get the answer. But there is a quicker way to do it. You can leverage some efficiencies by, instead of going from each starting point to the end point, you can flip your logic and set a constant starting point of the end point and find your way to each of the A points, and then get the shortest one of those, basically. And that you can leverage some efficiencies, because if you're going from that point E, all of the paths as you come out of that top point will all be the same for multiple different iterations. So you can cache values and stuff, and you can end up working it out much quicker. I didn't do that. That was mostly because I didn't want to rewrite all this checking logic. I just wanted to basically reuse exactly everything that I had, to be able to just run it over and over again and get the answer at the end just spat out easily. So it's a little bit lazy, but in this case, the laziness didn't actually kill my performance or anything in it, so I'm not too worried about it really, and I still got the right answer in the end. So that is it for day 12. It wasn't a crazy difficult problem. It was kind of a bit fun. There's always something with Dijkstra's algorithm. It comes up almost always in Advent of Code, I think. I sort of love-hate it, because I like when I solve it and I'm like, hey, I got it right. But I absolutely hate implementing Dijkstra's algorithm. Every time I go to implement it, I tie myself up in knots, and it takes me absolutely ages to get it right. So that happened today. I was just like forgetting how to do bits and then writing the wrong thing, and yeah, just a little bit of chaos, but got there in the end. So yeah, that just finished. 132 seconds to run, so just over 2 minutes to get to the answer for part 2. It's quite slow, but hey, it worked. It got there. And that's all that matters for this right now. We may be hitting the point of Advent of Code where these that'll do type efficiencies start to actually kill your ability to solve some of these problems. So we might have to start getting a bit more clever soon, but we'll see. Anyway, I hope you guys enjoyed, and I will see you all tomorrow for day 13. Bye bye.